So we left off with the dot product, right? The dot product, as just a quick reminder, turned into a scalar, right? We didn't spit out another vector. We spit out one number because we just added. That was by definition. Mason the other day was like, hey, it's kind of weird. Why did we go from multiplication to adding? And I have no answer to that besides that's just how it's defined, right? That's how the dot product happens to be defined. So that's what we do. And then we had two vectors are perpendicular if and only if their dot product is 0. And it turns out we have another way to kind of multiply vectors, and that's the cross product. So when doing the cross product, unlike the dot product, we get another vector spit out. So when we take the cross product of two vectors, we get another vector. And then the vector that you get from taking the cross product is automatically perpendicular to the plane created by the other two vectors. So what that means is any other two vectors you have, right? If I have a vector this way and a vector this way, together they kind of make up like a plane, right? Like an XY plane. And the new vector would be perpendicular to the plane. So it would be like if these two happen to be flat, right? Like if you can imagine this being a flat plane, the new vector we get would be straight up out of it, right? So maybe if you can see my face, this is the plane. If my hand is the plane, right? The new vector we create is going to be perpendicular or 90-degree angle to it. I'm not too good at drawing those things, but that is the best I can do for that. So, and this is what it's defined by. So the cross product is defined as follows. We have vector A and vector B, A1, A2, A3. A cross B, that's how we read this, by the way, right? So the other one we would say A dot B, that's for the dot product. For the cross product, we say A cross B. And we get this symbol. Now, I don't know how far you guys got in Integrated Math 3, but this comes from a matrix, essentially. This is the determinant of a matrix. And so if we don't remember how to do that, we should definitely probably write this down. You did, Abby. That's why I said, they're kind of on the track when you were talking about the matrix. So now this is the determinant of a 3x3 matrix. And so I'm going to go through what this equals, and you most definitely probably want to write this down because I think it's easier to remember to go over how to do a determinant than give you guys the long thing. So what happens is you go along the first row. So I'm going to start at I here. And so I'm going to have I times, and then if I cross out the row and column I is in, and I have the determinant of what's left, A2, A3, B2, B3. Right? And now I'm going to go over to J. And matrices, when we take determinants, have this weird thing where we have like this plus or minus rule where this one starts positive, then it goes minus plus, and then it should basically alternate. So if this is plus, what's below it should be minus, plus, plus, minus, minus, plus. So essentially, whatever you have should be surrounded by the opposite sign. So what this is saying is we have to do minus J times, and then if I'm at J, I'm crossing out the row and column J is in. I said that backwards. The row and column J is in. And then what's left is A1, B1, A3, B3. And then we have a plus sign again. And we can move over to K. So plus K, right? And these are really should all be vectors actually. K times, so these probably should all be vectors as well. And then when I take out the column and row that K involves, we have A1, A2, B1, B2. And then the determinants for 2x2 matrices are the first diagonal multiplied together. So in this case, it'll be A2 times B3, and then you subtract the other diagonal multiplied together. So I know that this is a lot of information to review or maybe to learn right away, which is why I saved this just for an example today. And then that would be I minus this diagonal multiplied minus the other diagonal multiplied, J plus this diagonal multiplied minus the other diagonal multiplied. Never learned taking the determinant of a matrix. We can this doing it with general variables makes it very confusing. So maybe after we go over the next example, it'll be cleared up quite a bit. And if it's not, this is actually perfect that we like kind of sped ahead. Maybe I can take Friday to just go over determinants and how determinants work. Oh, integrated math 3. Does algebra not get into college algebra? Crap. Did you guys have? Let me see. Did you guys have this book for college algebra? Is this what you used last year? Has anyone gone over matrices and determinants? It's in chapter 7, so maybe you guys didn't get there, especially with how last year went. Okay, so I'm gonna go through the next example anyway, and then maybe Friday I can spend that day going over determinants of matrices. It is in chapter 7 of this book though, so you might have gotten it. Maybe not. Maybe you guys decided to, bro, what is a matrix? Okay, so yeah. Okay, tomorrow I will spend the day tomorrow, maybe a crash course on matrices and determinants. This is, I think, really the only time you're going to need to know that in this class, if I'm not mistaken. But let's just get through this second example. So find the cross product of V and W and verify that they are perpendicular. So let's do V cross W equals, then we have this determinant thing where we have I, J, and K, and V is 0, 3, 1, 0, 1, 2. And now what we can do is if we choose this row I, then we are going to get, and if we pretend to cross out the column, the row and column that's in, the matrix that's left is 3, right? If I cross out the JK and the 0, 0, I get 3, 1, 1, 2. I minus, because it starts out plus, then it goes minus plus. Then if I cross out the J column and the row, what's left is 0, 0, 1, 2. You okay? Okay. Um, anyways, and then plus, and then if we take out that row and column, what's left is 0, 3, 0, 1. Okay. All right. So, and then what's left? So I'm crossing out the row and column with k in it, and I'm left with 0, 3, 0, 1. And then we multiply that by k. And then the determinants of these smaller matrices, you multiply these diagonals. So 3 times 2 is 6, minus 1 times 1 is 1, minus 0 times 2 is 0, 0 times 1 is 0, 0 times 1 is 0, minus 0 times 3 is 0. And so really all we get is 6 minus 1, which is 5i, plus 0j, which really just goes away, but and then plus 0k. And so when we put that back into a vector, that's just 5, 0, 0. So when we take the cross product, we spit out another vector. So the actual math of it, right, isn't hard, but like taking a determinant might feel a little wonky. We can work more on this tomorrow. And then it said verify that this vector is perpendicular to these two. And so if we do 5, 0, 0 dot first vector v was 0, 3, 1. And test that out, then we get 5 times 0 is 0, plus 0 times 3 is 0, 0 times 1 is 0, equals 0. And remember, when it equals 0, that means it's perpendicular, so that checks out. And then the other one to do, if we take the dot product of 5, 0, 0, and the other vector was 0, 1, 2. Right, then we get 5 times 0, which is 0, plus 0 times 1, which is 0, plus 0 times 2, which is 0, which equals 0, which again means it's perpendicular.